Hey you guys, this is Mr. Millings, and in this video we are going to learn how to calculate the heat of solutions. That is to say, the amount of heat that is either released or absorbed during the dissociation of ionic compounds in water. So let's jump right in and start talking about heat of solution or enthalpy of solution, and then let's work a few problems out together. So what is heat of solution? Well, it says right here, the heat of solution, or enthalpy of solution as it is sometimes referred to as, is the amount of energy associated with an ionic compound dissolving in water. And so when an ionic compound dissolves in water, it dissociates into the ions that make it up. And there's a specific amount of energy that is either released or absorbed during the dissociation process as chemical bonds are broken between the atoms in a solute. And so this is known as the heat of solution. So essentially, when we dissolve an ionic compound in water, it's going to dissociate. Right? The chemical bonds between those ions in that solute are going to be broken, and so a certain amount of energy is either going to be released or absorbed. And so that is what we're learning about in this video. We're trying to calculate the heat of solution or enthalpy of solution, the amount of heat that is either released or absorbed when ionic compounds dissolved in water. And so to figure out or to calculate the heat of solution, it's simple. We take the sum of the change in heat of our products minus the sum of the change in heat of our reactants. And so the heat of solution is the total amount of energy released or absorbed during the dissociation of ions in water. And if we take a look, the heat of products is the total amount of energy released or absorbed by an ionic compound as it dissolves in water. And the heat of reactants is the total amount of energy necessary to form each reactant. And so if we know this stuff by looking at a heat of formation table, then we can quite simply determine what the heat of a solution is. But let's visualize this. Let's visualize this definition. Let's visualize this chemical or this equation right here, or formula right here. And then let's apply this to a couple of different example problems. So let's learn how to calculate heat of solution. And so let's look at a couple of different examples. Let's first look at an example where we're going to take sodium hydroxide solid and put it in water. So we have an ionic compound here which consists of positive sodium ions bonded to negative hydroxide ions. And when we put this in water, it's going to dissociate. It's going to dissociate into 1 mole of sodium ions and 1 mole of hydroxide ions. And so how can we figure out the heat of solution here, or the enthalpy of solution? That is to say, the amount of energy that is associated with the dissociation of this compound into these ions right here. Well, to get that, what we have to do is figure out the sum of the change in heat of our products minus the sum of the change in heat of our reactants. And what we can do is use this heats of formation table. And so in this problem right here, to get the heat of solution, we simply take the sum of the change in heat of our products, and we find products to the right of our little arrow here, and our products, according to our balanced equation right here, is telling us we have 1 mole of sodium ions being produced, so 1 mole of Na plus ions. And if we take a look, how much heat is associated with the formation of sodium ions in solution? Well, if we take a look at our table right here, this is telling us negative 239.7 kilojoules per mole. And because we're asked to take the sum, we now need to figure out what it is for hydroxide. And if we take a look, there's an imaginary 1 here. So we're going to put 1 mole of OH minus. And we're going to multiply this by, you guessed it, the heat of formation of our hydroxide ions in solution, which if we take a look is negative 229.9. Negative 229.9 kilojoules per mole. And so that is just going to be the sum of our change in heat of our products. And we're running out of room, so I'll put the rest over here. Now we're going to subtract the sum of the change in heat of our reactants. And if we take a look, our one reactant here is sodium hydroxide, and we have 1 mole of NaOH. And now let's take a look at our heat of formation of NaOH. If we take a look, our heat of formation of solid NaOH is negative 426.7. And so now we just simply take a calculator and let's figure out what our first bracket is. We're going to subtract our second bracket, and that is going to give us our final answer, which we will end up putting right down here. And so if we take a look, we'll do this first bracket right here, and we're going to end up with negative 469.6 kilojoules, and we're going to end up with negative 426.7 kilojoules here. And so now we'll get our calculator out and subtract these two terms right here, and we're going to end up with negative 42.9 kilojoules. And so what does this answer mean? Well, this means that when we take sodium hydroxide and we place it in water here, it looks like it's going to release 42.9 kilojoules. This negative sign means that energy is released, right? So it's going to release 42.9 kilojoules as it dissociates into these ions. If we take a look at this example right here, if we take a look here, we have calcium hydroxide that we're going to put in water, and it's going to dissociate into these two ions right here. So how can we calculate the heat of our solution, or the enthalpy of solution? We use this formula, and so to get our heat of solution, we're going to take the sum of the change in heat of our products. And so if we take a look, our products from our balanced chemical equation is telling us we have 1 mole of Ca2 plus ions. We're now going to multiply this by the heat of formation of our calcium ions, which it tells us right here is negative 543.0 kilojoules. We're going to add this to, if we take a look, we have 2 moles of hydroxide ions that are being produced, so 2 moles of OH minus. And if we take a look over here, OH minus is negative 229.9. So we'll do our other bracket down here. Let's do our reactants now. Our reactant was calcium hydroxide, and if we take a look at our balanced chemical equation, we have 1 mole of calcium hydroxide and what we're going to do is we are going to multiply this by the heat of formation of calcium hydroxide. If we take a look here, it's going to be negative 986.6, negative 986.6 kilojoules per mole. And so let's figure out what's in our first bracket. We'll subtract our second bracket, and that is going to give us our heat of solution here. And so it looks like if we take a look, our first bracket is going to end up being negative 1002.8 kilojoules. And our bracket right here is going to end up being negative 986.6 kilojoules. And so we'll put this in our calculator. And we're going to end up with negative 16.2 kilojoules. And so it looks like when we dissolve calcium hydroxide in water, it's going to produce these ions right here. And when this dissociates, it's going to release 16.2 kilojoules of energy. All right, so let's go ahead and apply this concept to do 2 different example problems, and hopefully you catch on. In this example right here, it says to calculate the enthalpy of solution for the dissociation of ammonium nitrate. So what's happening here is we have ammonium nitrate solid, and when we put ammonium nitrate in solid in water, it's going to dissociate. We have an ionic compound right here, and so it's going to dissociate. It's going to break apart into the ions that make it up. It's going to produce ammonium ions and nitrate ions, and what we're trying to figure out is how much heat or energy is going to be released or absorbed when this dissociates into these ions in solution. And so if we take a look to figure out the heat of our solution here, we take the sum of the change in heat of our products minus the sum of the change in heat of our reactants. And so to get the heat of solution here, we're going to take the sum of the change in heat of our products minus the sum in the change in heat of our reactants. And then that should give us our final answer. And so Let's go ahead and do this here. Let's first work on our products. Our products are everything to the right of that arrow. We'll start off with a bracket. And so what this is telling us is that we have 1 mole of ammonium ions here, according to our balanced chemical equation. So we have 1 mole of NH4 plus. And if we look at our heat of formation table and we find ammonium, let's take a look at ammonium. Let's see if we can find it on our table. We see it's right here, negative 132.8 kilojoules per mole, negative 132.8 kilojoules per mole. So that is the amount of energy associated with the formation of ammonium ions in water. And so now what we need to do is we need to add this to our nitrate ions that were produced in water. And so if we take a look, we have 1 mole of NO3 minus ions according to our balanced chemical equation in this solution here. And then we're going to multiply this by our heat of formation for these nitrate ions. And if we take a look, it's negative 206.6. Negative 206.6 kilojoules for every mole. And so that's just going to be our change in heat of our products. What we now need to do is subtract the change in heat of our reactants. Our only reactant is ammonium nitrate. And if we take a look here, we have a coefficient of 1. So what that means is we have 1 mole of ammonium nitrate. And we're going to multiply this by the heat of formation of our ammonium nitrate, which is negative 365.1 kilojoules per mole. And so let's figure out what this first bracket is going to be. And then we'll subtract our second bracket here. And that's going to give us our final answer. And so if we take a look, our first bracket is going to end up being equal to negative 339.4 kilojoules. And if we take a look right here, this bracket is going to be equal to negative 365.1 kilojoules. And so we'll take this and put this into our calculator. And we end up with 25.7. 25.7. So our heat of solution is going to be 25.7 kilojoules. And so what does this answer mean? Well, what this answer means is that when we put this in water and it dissolves and forms these ions right here, energy is going to be absorbed from the surroundings by the system, right? Because the sign of this is going to be positive. Our final answer is positive, which makes this an endothermic process. And so when we do this, if we were to go into the lab and do this, we would feel this as being cool to the touch, right? The temperature would decrease just a little bit of that solution. The temperature would decrease. Let's take a look at a second example. In this second example, it says we have 255 grams of magnesium chloride dissolving in 3,750 milliliters of water at a temperature of 34 degrees Celsius. We want to determine the final temperature of our water. So it looks like we're dissolving some magnesium chloride in water. And what we want to do is we want to figure out what the final temperature of the water is going to be. So when we dissolve magnesium chloride in water, the temperature is going to change. The temperature is going to change as this magnesium chloride dissociates in water and either releases or absorbs energy, right? And so if we can figure out how much energy the water is either releasing or absorbing from the dissociation of the magnesium chloride ions, then we should be able to figure out the change in temperature. So in this problem right here, what we need to do is break this up into 3 steps. What we have to do is figure out the heat of solution first, based on our balanced chemical equation that we see right here. Once we're done doing that, what we then have to do is we will have to figure out the heat of solution based on our given quantity right here, which is 255 grams of magnesium chloride, based on a given amount, we'll just say. And then once we're done doing that, what we will then have to do is we will have to calculate the change in temperature using Q equals C times M times delta T. So we're going to solve for delta T in our final step and figure out what the change in temperature is, and then we're going to add that to our starting temperature, and that's going to give us our final temperature. So there's a lot going on here, so let's jump right in and solve this problem. In step one, what we're going to do is we are going to calculate the heat of solution. And so to get our heat of solution, here's our formula right here. What we're going to do is we're going to have to take the enthalpy of our products, and we're going to have to subtract we're going to have to take the sum of the enthalpy of our products, and we're going to have to subtract the sum of the enthalpy of our reactants. And so if we take a look here, if we take a look at our products, what this is telling us is that we have 1 mole of magnesium ions being produced, and we need to multiply this by the heat of formation of our magnesium ions. And so when magnesium ions are produced in solution, it looks like the amount of energy associated with them is negative 462.0 kilojoules per mole. And so because this is a sum here, what we need to do now is add our next product. If we take a look, what our balanced chemical equation is telling us is that we have 2 moles of chloride ions that are in our solution here. And so we need to multiply this by our heat of formation of chloride ions, which, if we take a look right here, is going to be negative 167.4. Negative 167.4 kilojoules per mole. We will close this bracket, and so here's our the change in heat or the enthalpy of our products right here. And so what we now need to do is subtract the enthalpy of our reactants. And if we take a look, our only reactant is magnesium chloride, and there's an imaginary 1 here, and what that tells us is we have 1 mole of magnesium chloride, and we're going to multiply this by magnesium chloride's heat of formation, which is negative 641.8, negative 641.8 kilojoules per mole. So there we go. Let's take a look now, and let's figure out what our first bracket is going to end up being, and then we'll figure out our second bracket. If we put all of this into our first bracket, what we're going to end up with is, let's take a look here. Negative 796.8 kilojoules here. And if we take a look right here, we're going to end up with negative 641.8, negative 641.8 kilojoules here. And so when I subtract these two numbers, we will end up with negative 155. So this is not our final answer. This is just the heat of our solution, the enthalpy of the solution here. That is to say, the amount of energy that is released, because the sign is negative, when the magnesium chloride dissociates to produce 1 mole of magnesium ions and 2 moles of chloride ions. So what we now need to do in step 2 is we need to apply what we got in step 1 to the given quantity. Okay, so let's go ahead and do that to get our heat of solution here. We are starting off with 255 grams of MgCl2. And what we need to do here is convert this to moles of MgCl2. And so we know 1 mole of MgCl2 from our periodic table of elements is 95.21 grams of MgCl2. So how did I get 95.21? Well, magnesium, if you look on your periodic table, is 24.31. Chloride, if you look, or chlorine, if you look on your periodic table, is 35.45 times 2. Add those together, and you get this right here. And if we take a look, for every 1 mole of magnesium chloride from our balanced chemical equation, for every 1 mole of magnesium chloride, it looks like we're going to end up with negative 155 kilojoules of energy, or 155 kilojoules of energy that is released when we start with this much magnesium chloride solid, right, and dissolve it in water. And so this is the amount of energy that's released, right, when this here dissociates and dissolves in water. And so now we get our calculator out. We take 255 divided by 95.21 times negative 155. And we're going to end up with negative 415.1. Negative 415.1 kilojoules. So this is how much heat is, or energy is going to be released when we have 255 grams of magnesium chloride dissolving and dissociating in water. It's going to release this much energy. And so let's think about this. If this is the amount of energy that is released by the magnesium chloride, well, what's going to absorb that? The water is going to absorb that, right? So this is kind of a problem where we have negative Q equal positive Q. The amount of energy or heat that the magnesium chloride is releasing as it dissociates in water is going to be equal to the amount of energy that the water is going to absorb from that. So in our final step, what we can do is we can use Q equals C times M times delta T, and we're going to solve for delta T. And so if we manipulate this formula, delta T is going to equal Q over C times M. And if we find the change in temperature, what we can then do is add that to the starting temperature and get our final answer. So Q is going to equal this right here, right? This is the amount of energy that the water is going to absorb. So the sign is going to be positive, not negative. So we have 4,115.1 kilojoules that water is going to absorb from the dissociation of these ions, or of this solid magnesium chloride into these ions. And we're going to divide this by the specific heat capacity of our water, which in an earlier video we learned was 4.18 joules per gram degrees Celsius. And we're going to end up multiplying this by the mass of our water. The density of water is 1 gram per milliliter. And so if we take a look, we have 3,750 milliliters, which means we have 3,750 grams. And so before we can put this in our calculator, take a look at the issue. This is in joules, this is in kilojoules. So we can't put this into our calculator yet. What we have to do is convert this to joules first. And so if we take a look, we slide this decimal to the right 3 times, and we have 415,100 joules. And we're going to divide this by the specific heat capacity of water, which is 4.18, times the mass of the water, which is 3,750. And so when we put this all in our calculator, we will end up with 415,100 divided by 4.18 times 3,750. And we will end up with 26.5 degrees Celsius. So this is still not our final answer. This is just the change in temperature. So how do we get the final temperature? How do we get final temperature? Well, if we recall, the change in temperature is equal to T final minus T initial. And if we manipulate this formula around, then what we will end up with is T final equaling our change in temperature plus our initial temperature. And so if we take a look, our change in temperature was 26.5 degrees Celsius. What was our initial temperature? Take a look right here. It tells us was 34 degrees. We'll put this in our calculator, and we will end up with 60.5. And so this right here is going to be our final answer to this problem. So a lot going on, but take a look. When we dissolve 255 grams of magnesium chloride in this much water right here at a starting temperature of this, the final temperature of that water is going to be 60.5 degrees Celsius. When you dissolve this in water, the magnesium chloride is going to dissociate, right? It's going to release energy. It's going to release this much energy. The water is going to absorb that energy, and so we can figure out delta T from there and then figure out what our final temperature is going to be. So if you like what you see, go ahead and click that little bomb in the bottom right hand corner, and feel free to leave any questions or comments in the questions section down below or comment section down below. And I hope you guys found this helpful.